Hello and welcome. So we're going to be proving some similar triangles today. So first off, just a couple of quick reminders on vocabulary that we're going to need for the later part of this lesson. First off is a dilation. It's just a transformation that changes the size of an image, making it bigger or smaller, but doesn't change the scaling. Right? So for example, this was a dilation from our little triangle to the big one. You can see the image itself didn't change other than getting bigger, right? One vertex of the triangle isn't magically longer, right? And it didn't change any of the angles going around. All right, a reflexive property is a number is always equal to itself. It's one of those common sense things saying 4 is equal to 4. That is true due to something called the reflexive property. The next is the transitive property, another one of those common sense things. Let's say that x equals 4 and y equals 4. And let's say that z is also equal to 4. Right? So that then tells you that x equals y by the transitive property, but you could also say that it's also equal to z. It's just one of those things where if you have something or two things, minimum two things, that are equal to the same thing, then those are going to equal each other. And we can do that for as many things as we want, right? As many things as we want, that's called the transitive property. Now, the triangle angle sum theorem is a little bit of a mouthful, but that essentially says that all of the interior angles of a triangle are going to add up to 180 degrees. All right, another reminder on your congruency angles or congruent angles through to parallel lines cut by a transversal. So you have vertical angles, which we can see here is that green highlight, 3 and 1, 2 and 4, 6 and 8, 5 and 7. Right? We have corresponding angles. I like to call these matching corners. If you think of that intersection point between the transversal and the parallel lines, right? Top left 3 is congruent to top left 6, and so on. Then you have your alternate interior and exterior angles. Interior means inside of those parallel lines. Outside is that exterior. You can see marked by yellow, right? And then the interior but alternate sides of the transversal. So 4 and 5 are congruent, 1 and 6. Here, 3 and 8, 2 and 7. All right, so those are kind of like a lot of the vocab we've talked about, right? Just wanted to remind you you'll need it today. Now, similar triangles. Two triangles are similar if and only if there is a dilation, right? Dilation being that word we talked about up here, changing the size, that maps one figure onto the other, meaning in the new figure, corresponding angles are congruent, meaning they are the same. The angle sizes have not changed. And corresponding sides are proportional. Proportional essentially means that I can multiply the same number to each side of my triangle and get the other triangle. So for example, if I wanted to go from our small triangle to our big triangle, what number can I multiply 1 by to get to 2? Well, 2. Is that the same number we multiply every side by to get the other triangle? Yes, right? 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6. You'll notice all we did here was multiply each side by 2. That's what it means to be proportional, is that every side is getting multiplied by that exact same scale factor. Okay, and then we'll notice all the angles remain the same. So these would be similar triangles. Okay, now to denote similarity in triangles, we use this adorable little, didn't mean to cancel it out, adorable little squiggle there. So we could say that triangle, and then we state the vertices of that triangle. So triangle, whatever is similar to, that's what that means there, similar to triangle DEF. There you go. Now, for similarity, any rotation, reflection, or shift will not change the similar triangles. So for example, as I'm looking at, let me erase some of this extra stuff I have. If I wanted to go little triangle to big triangle, if I move the little triangle over here, are they still similar? Yes. If I reflected that triangle, is it still similar? Yes. Rotated? Yeah, that's still a similar triangle. No matter how you move these triangles, they're still similar. Keep in mind, absolutely, it's not going to change that. It'll change how you see it and kind of look at it, but it's not going to change the similarity itself. All right, so to prove similarity, we're going to focus on 3 main ways to do it. The angle is the first. Sometimes you can just get away with angle and not that third. and essentially says that all angles are the same. You are guaranteed similar triangles if all angles are equal. So for example, we have 36, 100, 36, 100. Is the third angle the same? Well, yeah, because if you think about it, all angles add up to 180 minus 100 minus 36. When we do that, we're going to get an angle measure of, hold on, 180 minus 136. Don't want to make a mistake there, 44. Okay, so 44 is this third angle. And you'll notice if we did the same calculation below, you'll also get 34, which means these two triangles, they match exactly. They are similar triangles. That's why sometimes you can get away with angle-angle similarity, is that, well, not sometimes, all the time, you can get away with it. If two of the three angles match, you have similar triangles. Okay? Now, how you state similarity is it doesn't matter which triangle you start with. I'm just going to start with this top one because I feel like it. So triangle and, I don't know, J, L, K. Sure. All right, so I went from J to L to K. That's what I chose. I can choose this in any order. I could have also said triangle L, J, K if I wanted to. Right? Whatever order I want to go in, that's what you choose for the first one. And then it sets the order for the next similarity statement. So now I'm going to the other triangle, and I need to correspond my vertices together. So J was the 44-degree angle, which means I have to start with U in the next. And then I went to L, which was the 100-degree angle, which is S in my other one. T was the 36, like K was the 36. So UST. And that is a good triangle similarity statement, right? As another example, if I did LJK, then that would have been SJ. Wait, I went to the wrong one. I was like, wait a second, SUNT. Okay, where it started at the 100 to the 44 to the 36. All right, just make sure that you are consistent in how you write it, and that's the main thing for triangle similarity. All right, now another example would be something like this. You can see only the 76. Do you have triangle similarity? Keep in mind, right here, these are vertical angles. We don't know what that measure is, but we don't need to know it to know they're the same, right? Because we know that vertical angles ensure that you have equal angles right there. So then we have whatever that third number is. I can find it using supplementary angles if I wanted to, right? But I know that 76 doesn't match 25 or 80, right? Two of the three angles are not going to match, which means the third won't match either, and you can just simply say not similar. Okay, so keep in mind, you don't have to know what that middle number is in order to find similar triangles with angles. All right, the next is side-side-side similarity, and you know this by saying the sides are proportional. All you need to do is you need to just compare the sides together and say, all right, do I have the same scale factor from one triangle to the other? If yes, they're similar. If no, they're not. Pretty straightforward. Now, keep in mind, you have to be very careful to stay consistent with your triangles. So for example, my smallest side here is 18. That can only correspond to the other smallest side on the other triangle, which is 6. Now, I like not having fractions, so I'm going to go the larger to the smaller triangles. I'm going to say 18 divides 6, we get 3. And then we just keep going. So the next biggest side is 24. Medium is going to have to correspond with our medium. 24 divided by 8, we also get 3. And then we have the larger side to the larger side. We have 27 divided by 9, we get 3. Now we'll notice that these are all the exact same number, which means yes, your two triangles, triangles FGE, is similar to triangle CDB. All right, and how I was able to write that without similarity, F was between my small and medium side, just as C was. And then I went to G, which was between my small and large side, which was D on the other, which means we had to go B as the last one. All right, now keep in mind for the other direction, just as another example, we'll do the same thing. Smallest to smallest, 45 to 10, which is, let's see here, 45 divided by 10, 4.5. Okay, the next number we have 12 to 55. Now I said 12 to 55, but notice I'm staying consistent. The larger number is on top. You have to, if you go from larger triangle to small, you have to stay that same way in your proportions. So 55 divided by 12 gives us 4.583 repeating. And right here, you can stop. You will notice they're not similar triangles because are those the exact same number? No, they're similar, but they're not exact, which means they are not the same scale factor and not similar triangles. Now, side angle side is the happy medium of these two things where you could say, okay, I like the angle, 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 and I like side, 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 but both of them together gives you side angle side. Now keep in mind, a side angle, that angle is between the two sides. That was very, very clearly placed there. In order to have triangle similarity with side angle side, the angle must be between the two sides. So notice here we have a side angle side, side angle side. That is always going to be the case. And if it's not, then you can't use side angle side similarity, right? So if my angle was up here, I would have had angle side side, right? That is a pain in the angle side side. That's not going to be able to do anything for you, right? You have to have the angle between the sides. And all it works is you say, okay, are the angles the same? Yes. Are the two sides proportional? So we'd say, all right, well, smaller to smaller. 40 divided by 4 is 10, right? Larger to larger, 60 and 6, which also gives us 10. Yes, these are similar triangles. The angle is the same. The sides are proportional. All right, so we could say triangle CDB is similar to triangle MLN. Whoops. There we go. All right, and there you have it. You have similar triangles. Now on this one, we don't see any angles. Do we know they're the same? Yes, right? Side, angle, side. Okay, and we know this is the angle between. That's the angle between. By vertical angles, your angle is good. That is the exact same angle as congruent by a vertical angle theorem. Keep that in mind. All right, so next we look at that and say, okay, proportional sides, 49 over 20, 39 over 16. Are those the same number? No, they are not, right? 49 and 20 doesn't simplify. 39 is not going to simplify with 16, meaning those are not equivalent fractions. Sad day, right? Not similar. Move on. Okay. All right, so for these two examples, you can just easily see here, this is notated saying that they are the same for us. So angle is the same. You would just double check for sides, saying small over small, right? So 7 over 35. And then you would say large and large. 8 over 41. Not going to simplify, which means not similar. That's as easy as it gets, right? Here we have side, 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 all three ways. Let's double check. 5 to 20. 5 to 20, and then we have 6 to 24, 6, 24, and remember you're staying consistent. As long as I do the same thing, all three sides, it should be fine. If you want to have the larger numbers on top still, you totally can. I just cared to see if I get the same number. 5/20 is 1/4, 6/24 is 1/4, and 8/32 is also 1/4. They all match. Yes, they are similar. State it as such. So triangle STU similar to triangle, let's see, B, CD. There you go. All right, so that's triangle similarity, how you determine it. All right, now how do you tackle two-column proofs with similar triangles? Well, first off, you have all this adorable information, it's all given to you, and you want to prove they're two similar triangles. You have three different ways to prove similarity. Angle, 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 side, 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 or side, angle, side. Look at what's given to you. Do you have any angles in there? No, meaning the only way you're going to be doing this is by side, side, side. meaning that you need to make sure that all of the proportions are exactly the same. And if you haven't proved that yet, then you haven't proved side, side, side. All right, so know where you're going to go from the beginning, and that will help you guide yourself through this. So R to S, we're told, is 6, QS 14, RQ 20, BC 42, BA 140, AC 98. All I did is I took this information and I just plopped it on my triangles. Okay, so all that same information, it was given to us, yay. Now, this next one, it's just leading us through this. A segment AB divided by QR. Okay, well, AB, we were told, was 140. QR, we're told, was 20. What is 140 over 20? 7. Okay, substitution, we just substitute those values in. Algebra, we simplify the fraction, right? And we're going to have that same reason on all three of these. So AC, 98. QS, 14. All right, now if we divide those two together, you're also going to get 7. And then BC, 42, goes to RS, which is 6, also 7. Now you'll notice we have proportion, proportion, proportion. Those are all the same value. How can I state that those are all the same value? Down here it gave us a hint. It said transitive property. Remember at the very beginning we said, hey, look at that like der moment. If all three things equal the same thing, then they're equal to each other, right? Essentially, we're stating that, yes, we can see it's all 7. We need to state that they're all the same number. They're all the same proportion now. So all we need to say in this next one is that our three proportions, AB over QR, is equal to our next proportion, AC over QS, which is equal to our next proportion, BC over RS. And we know those are all equal because they all equal the same thing, aka the transitive. Now remember, our goal was side, side, side. Do we have it proved when we know we have side, 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 all proportions the same? Yes. So now we can just state what we wanted to do from the beginning, are proving the similarity statement. Triangle ABC is similar to triangle RSQ. Oops. There we go. And we know that by side, 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 similarity criteria. There we go. Okay, and that's how you would go through a proof. All right. Yes, we can see that those are all equal to the same thing, but proofs literally take you baby step by baby step. You need to state that your proportions are equal to get the similar triangle. All right, let's do one more. This one with some angles, a little bit harder. So example 3, given 2 triangles, complete the proof for each statement or reason. Note triangles are not a scale. All right, so we're given this next symbol. That fancy thing there means parallel, which we can see with the arrows here. All right, and then we're given that angle ACB is congruent, that's what that means, to angle E. All right, and we can see that here. So we know that this angle is the same as this angle, congruency, we're guaranteed that. All right, now we're proving that a proportion AB over DC equals other proportion BC over CE. In other words, we need to prove that we have proportional sides. Okay, so in English, prove sides are proportional. Now, do we know the sides are proportional? No, we don't know the sides are proportional because remember, do we have anything given to us talking about side lengths? No, we only have stuff right now with an angle and something about parallel. All right, we know nothing about side lengths, but we need to prove that our sides are proportional, aka we need some side lengths. But keep in mind, this is back to a definition, is that 2 triangles similar if and only if, this means it's going to go both ways, right? If your angles are congruent, you can say that your corresponding sides are proportional. If you have similar sides, you are guaranteed proportional sides, all right? That means that to do this, we need similar triangles. Okay, so I know that my last goal, my very last thing, is to say exactly what I'm trying to prove, that AB over DC equals BC over CE. In other words, we know we need to prove proportional sides, and we know we're going to prove it because you have similar triangles. So ABC similar to triangle DCE. And I just got that from our second line that was filled in for us. Okay. Now, as I'm looking at this, no side lengths are given to me, meaning that which of our three criteria makes the most sense here? Are angles, angle, something with sides, or something with sides? Where we don't know anything with sides, your only option is to use the angle similarity, right? So we're going to say we have similar triangles by angle similarity criteria. All right. So there we go. We already know these last two lines because that's what our plan is. Now we just need to figure out how we know our sides are the same. Okay, so first off, it tells us two things that are given. What was given to us? Well, first off, we know that the segment AB is parallel to segment DC. That was given. We also have an angle, one of our three angles required, ACB, congruent to angle E. Now you might be wondering, that's nice. How do we get the other two angles? You'll notice a little hint here, corresponding. Remember, if you have two parallel sides, you are guaranteed 4 parallel theorems here. You have corresponding, alternate interior and exterior angles to work with. So let's start looking at what we have here. Oops, here we are. Okay, so to make this a little easier to see, I'm going to extend these in a different color. You can see this a little bit better. So the orange are our parallel lines, and the blue is our transversal. So my goal is I want to be able to say something about these angles, right? So if I'm looking at, let's say, this angle here, can I say anything about, let me use this in pink, knowing those two parallel lines and the transversal, can I say anything about that? No. But I can say from here is I'd say, okay, well, let's keep going. If this transversal is not really helping us, let's look at another transversal. Let's look at this one. So along this transversal, we have this one, and we want to talk about that angle. Does that look like any of our 4 theorems? Can we say anything about vertical angles? No, if they're not at the same vertex. But we can say corresponding angles with this one, can't we? Because we know that it's that top right and top right. So when you're looking at this one, try looking at both transversals, see which one does more for you. So in this case, we're going to talk about these two angles right here. Now we need to be a little more specific because angle C can refer to any of the angles there. So I'm going to use triple notation here. I'm going to say angle ABC to talk about that angle there, and triangle ACE to talk about that middle angle. Now for those angles, I'd say, okay, now what are we saying about them? We're saying that they're the same. And they're the same because they're corresponding angles. Now this next one we say, okay, angle BAC to angle CDE, meaning we're talking about this third angle here. Now we looked at that transversal and we said that we can't do anything with those two angles because that's not on the transversal. It's not in that vertex area, right? Which means what can we do? Well, keep in mind, you know 2 of the 3 angles in that triangle, right? Wouldn't you agree that if this was, these are just random numbers I'm going to pull up, okay? If this was like, I don't know, 100 degrees and this was like 40 degrees, couldn't you find this angle here? And we know those are congruent, so couldn't you just use your triangle interior angle sum theorem? Whew, as much as a word that is, because you know all angles in a triangle add up to 180. All right, so I don't know what those exact angles are. I don't need to know what those exact angles are. All I know is that I can find that third angle and it's guaranteed to be the same because we know 2 of the 3 match, right? So angle BAC and CDE are congruent by your triangle angle sum theorem. Okay? And now we know that 3 of your angles are congruent, which means that by your angle similarity, you have similar triangles. And because you have similar triangles, the sides are proportional, guaranteed. Okay, so take your time, make sure you know what you're trying to prove and how you're going to get there, what you're going to need for the in-between steps. I would start here, and then fill in the middle afterwards, right? So there you go. That is triangle similarity proofs with those 3 criteria. Thanks for watching.